We have a collection of various trigonometric functions, and we are going to try to match their graphs. Looking at this graph, it certainly looks like either tangent or cotangent. Notice the function is always increasing. As I move to the left, the graph is always increasing. And it's pretty rapid. Notice I have 3 cycles per pi, like from 0 to pi, there's actually 3 cycles. And so 0.3 tangent of pi x seems to match that. So this one is B. This graph looks to have a line of equilibrium, y equals 40, and an amplitude in the 30s, so 32 matches the amplitude. There's a horizontal shift, and if the horizontal shift was 2 and there was a minimum, then you could have cosine multiplied by a negative. So A seems to match that. I'm multiplying cosine by negative 32, giving me an amplitude of 32, and the negative flips the graph vertically. Notice the frequency is pi, so I'm actually getting a little more than 3 waves per 2 pi from 0 to 6. Notice I'm getting about 3 waves. And my line of equilibrium is 40. This graph looks to be just regular cosecant. I have vertical asymptotes at 0 and pi and 2 pi. The line of equilibrium appears to be y equals 0, and the distance between the bottom and tops of the u's looks to be 1. So C, basic cosecant. This graph appears to be either secant or cosecant. It seems like I have asymptotes at odd multiples of pi. It looks like there's an vertical asymptote at pi and a vertical asymptote at 3 pi. The middle looks like it's around -10, so say -9, and the distance between the bottom and top of the U shapes and that middle looks like it could be 7. So E appears to match this graph. Notice the 0.5 multiplying x slows down the cycles, and so I'm only getting 1 cycle per 2 pi. So if you look from 0 to 6, we're only getting 1 cycle, and it is shifted down to -9, and the distance between the -9 and the bottom and tops of the u's appears to be 7. This wave appears to have a line of equilibrium that is around -32, and -32 plus 40 would give me a maximum at 8, and the maximum looks like they could be occurring at 8, and it would give me a minimum of -72, and again that kind of agrees with what we see. Notice that the waves are fairly rapid. If I look from 0 to 6, I'm getting basically 3 waves. And D has a frequency of pi, so I should be getting 3.14 waves per 2 pi. And then there's a horizontal shift of -2. So at -2, I appear to be on a line of equilibrium at -32. This graph appears to be either tangent or cotangent. Notice the cycles are always going downhill. If I go left to right, I'm always going downhill. And the center, where the inflection points are, appear to be at 6. And J matches that, cotangent of 2x plus 6. Notice I'm getting 2 cycles per pi from 0 to 3.14-ish. Looks like there's 2 cycles, so J. Here I have a slight wave around a slanted line. So notice F has x added to the sine wave, and x is a line with slope of 1 that goes to the origin. Sine would be on the line of equilibrium at 0 unless there was a shift. So sine of x over 3 should be on the line of equilibrium at 0. The frequency is only 1/3, so I'm just getting part of a wave between 0 and 2 pi. And the amplitude certainly could be 2, so it looks like it's F. Inverse cosine, also called arc cosine, has a range from 0 to pi and a domain from -1 to 1. So cosine had a range from -1 to 1, so that's now the the domain of inverse cosine. And in order to make inverse cosine a function, we had to restrict it. And so the official restriction is to get outputs from 0 to pi. So this is definitely the graph of arc cosine or inverse cosine. This function has a range from negative pi over 2 to positive pi over 2 and a domain from -1 to +1. And arc sine or inverse sine has an official range defined for it to go from negative pi over 2 to positive pi over 2. So the measurements that you get for sine in quadrant 4 and quadrant 1. So that will be G. By process of elimination, we could figure out that this must be I because we didn't build in any extra graphs or formulas. But if you do look at the graph, you will notice that the amplitudes are getting higher. And if the amplitude itself is a function like a linear function 1/3 x, that is what would occur. So this must be I, and the amplitudes are given by the line 1/3 x. If you actually graphed 1/3 x and -1/3 x, you would notice that this wave bounces back and forth bounded between those two lines. Well, there you go. That was a nice set of review about graphs of trig functions.